Hi, I'm Lucas, and you're listening to Gradient Descent. We started this program because we're super passionate about making machine learning work in the real world by any means necessary. And one of the things that we discovered in the process of building machine learning tools is that our users and our customers, they have a lot of information in their heads that's not publicly available. And a lot of people that we talk to ask us what other people are talking about and what other people are doing, what are the best practices. And so we wanted to make all the interesting conversations that we're having and all the interesting things that we're learning available for everyone out there. So I hope you enjoy this.
Today our guest is Nicolas Koumchatzky, who is currently a director of AI infrastructure at NVIDIA, and before that ran Twitter Cortex and was one of the first people to put deep learning models into production at scale. So Nicolas, thanks so much for taking the time to talk with us. I mean, you're an expert on deploying deep learning in the real world. And I would love to, kind of just hear how things have changed since you've been doing it. I mean, I think you started doing this in like 2016 or maybe even earlier at Twitter. Like, kind of what were the challenges then and what are the challenges now that you're seeing in making these models actually work?
Thank you, Lucas. I started learning, by the way, about deep learning in 2014. So I'm not one of the old schoolers of deep learning, unfortunately. But then I get hooked up pretty quickly.
Yeah.
And then I started in a small startup with 5 people, something like that. And we were acquired by Twitter. At Twitter, we started this first deep learning team, basically.
Uh-huh.
And so at Twitter, basically Twitter didn't have any deep learning knowledge back then, or very little. And so we were associated with software engineers there in order to productionize deep learning on some product areas that could benefit from it.
And what were the first areas where they felt like they could get a benefit? Was it vision stuff?
Yeah, kind of a mix. Mostly vision, yes, and text.
Uh-huh.
So we started with two main projects. One of them was filtering out kind of like bad image content,
Uh-huh.
So that was one. And the other one that was more like a good product feature, basically, was deciding whether a user profile was safe to place ads on it or not. And this is a big deal for advertisers because they wanted to make sure that they could put ads on profiles and make sure that these profiles are not like toxic or insulting or like all kinds of accounts that you don't want to put ads next to. And so we were able to classify those profiles using the text, using the images, using user features as well, which allowed us to put ads on profiles. As you can imagine, this was revenue generating quite a bit. And so, and so that was kind of like the beginning of this team. Yeah.
And so is this shifting from an existing, like kind of more traditional model to a deep learning model, or like a new deployment of like a new problem?
No, in those cases, there had been interest in those areas, but without deep learning, it was almost impossible to perform at the required accuracy. So, for example, advertisers expect like 99.9% accuracy, right? It was unachievable just using tabular features and decision trees. I mean, I think it would be doable if one put the effort, but much more complex. So.
And I guess like these sound like applications that you could do as sort of a batch process in the background, like it doesn't need to run live on user queries, or does it?
That's true. Doesn't have to. You're right. Except potentially for filtering of images. So when a user posts an image, make sure that those images are kind of like hidden right away. For example, for certain categories of user. One thing that required a lot of real-time processing was us catching kind of like very bad images. I'm not going to go into details, and we wanted to really do that in real time before they hit the platform, basically. So in that case, we would have a budget of like 100 milliseconds, maybe, or 50, even less than that, right? To be able to get them.
Wow, this is like 2016. So I mean, how did you get that working in real time in production? Like what?
Right. So that was interesting. I'm sure you know the details of like deep learning frameworks back then, but basically there was Theano and LuaTorch. And so we were using LuaTorch.
Cafe? No, there's no.
Oh, and Cafe. That's true. Cafe. Yeah, right. Forgot about Cafe. We were using Cafe, although it would have been a pretty good solution in that case. We were using LuaTorch. And so what we did for model training, it's great. However, for deploying to production, it's kind of more difficult. So we basically took what we had and wrapped it up into Scala services. Yeah, that was so much effort, basically. So much effort to make sure it was working, stable, and so on and so forth.
Wait, so did
Now,
you actually run Torch then in production, or did you like
yes,
compile it?
yeah, we were running Torch in production. Yeah,
Wow.
yeah, that was a lot of effort, right? So it requires so much engineering.
And you have 50 milliseconds to make a decision. That sounds like a real feat. Were you doing that, or were you kind of handing it over to a different team to deal with?
No, we were doing it internally, right? No, we had to because it required a lot of expertise, but deep nets, right? And what could make them go faster or slower, the batch size, all those things, right? So we had to do everything in house.
And were you like retraining live too, or how did that work?
So we did that, but later. So that was the first part where we used deep learning only for images and text mostly, right? Look at abusive content, for example, and so on and so forth. But then, after a little while, we started looking at other problems that were more fundamentals to Twitter, like ads placement, timelines ranking, things like that are more tabular based, right? So like using user features, item features, and trying to make the best prediction of whether a user is going to engage with some content. And we also managed, we use deep learning for that too, and we managed to get better results than traditional techniques, basically. And so the reason why I started with all of that is because in that case, for example, for ads placement, it's very important to have access to the latest and greatest features. And so to do online learning, what we call online learning, which is, yeah, like learning continuously or like with very high frequency, because otherwise there is a quite like quick decay of performance, right? The decay, the half-life, I don't know, maybe something like 1, 2, 3 minutes, right? Something like that. And then the model starts to decay. Yeah. So we had to do online learning for that, yes.
Wow, so you would retrain every minute?
So so there are multiple ways of doing it. One way to do it is just to do online learning right away. So just keep training.
Yep.
Online. You could also like freeze some of the layers and only retrain the last logistic regression, for example. So this is the easiest one, I think, actually. So you can learn some kind of a like wide, I don't know if you're familiar with wide and deep architecture, for example.
Yeah.
But yeah, you could use the like the memorization part, right, which is usually where the decay happens, and keep retraining that one basically, and keep the other one constant. Or I think some companies do that. I think Google does that, for example. I'm not so sure, but they retrain regularly, like every 5 minutes maybe. So they take the existing model in prod, fine tune it, redeploy, fine tune it, redeploy. Yeah, so that's possible.
Do you ever go back and like sort of retrain it from scratch, or is it always just sort of like online?
Yeah, we do mostly if we want to add new features or radically change the model architecture. Right. Yeah.
Excuse me. How do you even I guess how do you even evaluate then if like a new architecture is going to be better? Like it seems like that would be kind of tricky, right? Like how do you?
Yeah, so we have to simulate the fact that it's online learning basically. And so in that case, there has to be like a time period where we say, okay, we stop training and we look at everything that's after, and then we can evaluate by keeping learning. It's possible to simulate the situation basically, right? By replaying. But it's more infrastructure basically. Yeah.
Wow. And so I mean, this must have been an incredibly high amount of compute.
It's pretty high back then. Yeah. I mean, interestingly, old CPU though.
All CPU.
Yeah, all CPU because GPUs were not. I mean, I work at NVIDIA now, but they were not that easy to use in that context. There was less tooling. Now it's changing with. I don't know if you heard about Rapids, for example, or so basically data science accelerating on GPU. There are a lot of libraries available now, but back then there was none of that. So we had to we accelerated code on CPU basically to make it really, really fast. Yeah.
And were there other pieces of infrastructure that you had to build to get this working in 2016?
Oh yeah, 2016. Well, so you mean besides the inference serving actually?
Yeah.
I think we had to for the training part. One of the challenges we had is that a lot of our customers were used to decision trees and certain APIs and configurations. They were not familiar with Lua Torch. Few people are familiar with Lua in general. So we kind of had to hide this under like, configurations. So we built infrastructure to basically simplify their life such that they could copy paste configurations, right? And just specify their features basically. So it's like, okay, these are the features I have. These are the steps I want to run, like training, validation, whatever. And then basically, basically like automatically save their model and so on. So we brought a lot of like automation in the training phase at the cost of flexibility at the beginning. Then it changed, but yeah.
And how did it change? Like, how did it evolve?
So then once the company started realizing the impact and the importance of this at Twitter, they decided to also hire people who could understand and really invest in education. That was one. And at the same time, we decided to, like as the centralized machine learning platform team, basically to move to TensorFlow. Why TensorFlow? Because back then PyTorch was still very kind of like new and unstable, not even 1.0, I think. And so moving to TensorFlow, which also had like an inference story, right? Which PyTorch doesn't have, and so on and so forth. That's why there are so many recommender systems using TensorFlow those days, right? Because they have like this complete story. Anyway, so we moved to TensorFlow pretty quickly after that for training and inference. Yeah.
I see. And
training at least, not inference. Anyway.
No, not for inference.
No, I mean, some part of it, just the library part, just the C++ library part. But the thing is, Twitter has their own data formats and serialization formats, so they had to play with that. So, for example, Thrift instead of Proto, right?
Yeah. And were there any? I guess, are there any other sort of like surprisingly challenging things at that time, like stuff that like maybe like academics or people that don't work in these sort of large scale deployments wouldn't know about? Like any other like tricky pieces?
So you mean from Twitter people?
Yeah, Twitter. Yeah.
I think in some parts there was a disbelief about around deep learning. This just I don't know if that's what you're asking exactly, but and I think it still exists in the medical field, for example, where people ask for interpretability or explainability and so on and so forth.
Yeah.
And even at the expense of better performance, model performance. But eventually that disappeared basically. Like,
it's so funny. In like 2005, I worked at Yahoo moving models from like rule-based ranking systems to boosted trees.
Yes.
And they had all the exact same complaints. Like people were like, "Oh, these models are unexplainable. They're like impossible to deploy. Like it's like making like chaos in our infrastructure." It's like exactly the same, but now they have the same complaints about moving away from decision trees. So.
Yeah, exactly. Well, the difference for the infrastructure is that we replicated almost the same APIs as what Twitter had for decision tree. So it was a little bit easier. There was already kind of ML ready.
Right.
Whereas in your case, I guess it was like completely different, right? I'm sure.
Yeah, but it sounds like you had to kind of add some weird components and sort of abstract it away in the same way that.
Just basically abstracted everything away and made it look the same, basically, to gain adoption. that was fun. Yeah.
So when did you move to NVIDIA?
That was like a year and a half ago, 18 months.
And so tell me about the stuff that you've been working on at NVIDIA.
Yeah, so it's quite different in terms of the application domain. However, I'm basically managing the team, building the platform managing the team, building the platform to develop autonomous vehicle software. So, and in autonomous vehicle software, I also include like deep neural networks, right? Like all the validation required for it and so on. So this is what I'm managing, and it's a pretty big endeavor. The reason for that is autonomous vehicles are such large scales. There are so many models, so many people working on it, and there are so many specific needs that we have to build relatively custom infrastructure in order to be able to to be efficient and good at it and competitive.
And do you mean it's like custom infrastructure for self-driving cars, or custom infrastructure for every individual team working on self-driving cars?
It's the nature of developing models and what we call perception. So the ability to understand the world, from a car. So multiple models plus custom modules and so on and so forth. Developing this requires a lot of customization in the cloud infrastructure. Basically, is what I'm saying. So as an example, all machine learning teams use some workflow system in order to say, hey, I want to do this task and then do this task and then another task, right, and so on and so forth. In the case of autonomous vehicles, the big difficulty is that they are going like the various steps are going to be in so many different languages so many different libraries. So one is going to be like data preparation using Spark. One is going to be like, oh, now I want to run the actual software from the car on the target hardware, right, which is the actual embedded hardware that's racked in the cloud. But I want to run it on this, using CUDA, and then I want to run a Golang container. So all of these things are so different that they require a workflow system that's agnostic to all of this, and that can be deployed on heterogeneous hardware. I mean, bypassing the details, but basically, in some aspects, we had to develop our own customized infrastructure. Yeah.
Got it. And so, like, what? I guess you were sort of starting to talk about this, but what are like sort of the big components of the infrastructure that you build, and what are the big problems that each component solves?
Yeah. I mean, at the top level, so where we interact with our users, we really provide tools and SDKs and libraries. So that's the top level. At the bottom level, we have really core components that enable this top level. So at the top level, what we do is we go from everything outside the car. So when people drive, like drivers basically collect data or test a new build of the software system. Then they take out the data or send it over the Wi-Fi. Then it gets into the system. It needs to be ingested. So that's the first step, ingestion. Ingestion is already pretty complicated because it's similar to like Yahoo or Twitter, where you need to write heavy and then have some way to like process the data once in a while to transform it into data sets that are more consumable by downstream users. We have to do that. The challenges are pretty massive because we need to test for data quality, for example, or we need to index the data. We need to process raw data to transform it into something that's easier to consume downstream as well, and so on and so forth. So that's the first step. Second step is to build the best data sets, and that's actually a big challenge. The way we approach it is that, I mean, I'm sure you're familiar with that, but we view like machine learning as like software 2.0, like as Karpathy like kind of laid it out. I don't know if he was the first, but where data is the source code of machine learning. And so we need to be very careful about how we write our source code. And in order to do that, we're developing tools to curate data sets. So like create data sets, select the right frames, the right videos, with the right filters, make sure there's no overlap between training and validation. So we have a lot of tooling for that.
And so these are tools, they don't actually do this. They like help a user pick this, or do they somehow automatically like pick the...
Well, so both actually. We also investing a lot in active learning. Since you were at Figure 8, I'm sure you have a lot of experience there.
Sure, but I'm always fascinated by how other people do it too.
We published a blog post recently exactly about that, basically, where autonomous vehicles is perfect and lends itself perfectly to active learning. Massive amounts of data, but very costly human labeling, right? Right. So if you want to do 3D cuboid labeling, it's so costly. However, there are like, thousands and thousands of hours of data of driving available. And so we really have to select the one that's going to be the most efficient, and that's going to find the pattern that the DNN, deep neural network, is not able to find. And in order to do that, we use active learning, and active learning basically gives us like uncertainty scores, right? And the frames or videos with the highest uncertainty are basically the ones that we're going to want to label in order to improve the performance. And so we tried it, and we get like a 3x higher improvement, 3 to 5x actually, higher improvements using active learning sample data versus manually curated, not even random, manually, so like by humans, because...
So like humans like guessing what data is going to be the best?
Yeah, exactly. So they're like, the challenge was that, let's find VRUs, vulnerable road users, at nighttime. And so it's a super challenging problem because, of course, for cars, it's difficult to view at night, right, with the camera and so on. And in general, like, pedestrians and bicycles, basically, these are the two categories, are also difficult to detect. Anyway, so the idea was to detect these ones at best. So first pool was like manual curation. A group of people were told, look through the videos and find images that are relevant for these classes. And the other group was like just using the models for these specific classes, find the frames that have the highest uncertainty for these two classes, right? So one was completely automated. And we were able to find the frames that were very, very uncertain, basically for pedestrian and bicycles, right? Which shows maybe 20,000 of them. Then the manual curation did the same, 20,000. What they did usually is that they swipe through videos, and when they find pedestrians or bicycles at night, they just stop and they select like, a few frames in that segment of video.
Uh-huh.
And then we trained model with these two sub data sets. We looked at the validation performance, and validation performance was 3 times higher. I mean, the increase was 3 times higher for active learning selected data. Yeah, so it does work, and it can be completely automated if you think of it, right?
Wow, that's really impressive.
Yeah.
That's amazing. And that's in your blog post. We should definitely get a link to that.
Yeah. No, I can share that with you. I mean, we were impressed too, basically, because it was just an experiment, a research experiment. And now we're working to automate that and to be able to even automatically select data, retrain models, and improve performance. And we could have a machine fabricating DNS, right, basically, with human in the loop, just for the human annotations, basically. So that's
okay,
great.
what else? Sorry, I think
What
I
else?
derailed you. So there's data collection.
Then there's labeling, which I'm sure you're very familiar with because you're working at Figure It. But for autonomous vehicles, there are some pretty massive challenges. So first, the scale. Scale is massive, right? So NVIDIA has 1,000 plus labelers in India. Yeah, we're doing it ourselves. The software to actually be able to dispatch requests, right, to these labelers and manage it, as you probably know, is quite complex because it has to deal with human workflows, right, and the way they behave. So when they refuse, when they make mistakes, and so on and so forth, integrate quality assessment in the loop, and so on and so forth. So that's one. But also the tools themselves, the UI tools are pretty tricky. So for example, we need sometimes to be able to draw, like for example, 3D cuboids, and make sure we can link LiDAR data with image data, right? So we need to have a mix of like human labeling and like automated computing to be able to link these two things, for example, or like build a new representation of the data that is then usable by those humans. And I think the two at the same time is pretty complex and difficult to do. So yeah, so we built all that. So that's step number 3, basically, labeling of the data. Then step number 4 is about training. So we've developed a lot of code to enable our AV developers to train their models. One of the biggest challenges we have is that once we train, we need to export this. We need to do inference on an embedded system. And so we are compute constrained in a way. I mean, this is one of the constraints. We cannot deploy like 1,000 servers to be able to crush everything. We need to use a single chip to compute everything. So in order to make that right, we use multitask training, for example, where we have one single model body that can predict multiple things like path detection or obstacle detection or light sign, intersection, so on and so forth. Right? I think this is similar to what Tesla is doing. I know they've written a blog, they've done a talk recently talking about that. There's that, and then there's a lot of optimization such as pruning the models or int8 quantization or neural architecture search that we can use in order to even further reduce the size of the model with equal performance.
And so your tools do all of this? Like, is there stuff left for like a perception team at a customer to do, or like how do you think about that?
No. I mean, we provide this as part of the core libraries, but of course, sometimes they need to do something new. When they need to do that, they can add their own algorithm and so on and so forth, and then we basically productionize it, platformize it. Also, what they're really focused on the perception side is not really those features. It's more like, I mean, they're looking into it. That's very important, but also looking a lot into new types of predictions, for example. So they were predicting bicycles. Now they want to predict more fine-grained things, right? So they're going to have classes.
Yeah.
That's, they do a lot of those things, basically, that we don't have to care about. We just provide the core infrastructure. Yeah.
So you provide kind of core infrastructure to do multitask learning and quantization and things like that. But then the customer would sort of provide the different types of like classifications that they would want.
Yeah, exactly. But of course, like there's a small overlap between the two, and we help each other. Yeah.
Do you handle things like some of the newer stuff, like trying to figure out like intentions or like trying to actually like map out the sort of like underlying dynamics of like a person, like where their arms are and head is and stuff like that? Is that within your scope or?
Yeah, I mean, not my team specifically, but the perception team is definitely looking into things like that. Yes, that's usually more on the research side, a little bit more advanced, but yes, definitely, yes.
Okay, and is this does this work with different ML frameworks, or how does it? Is it like a lower level than that, or how does that work?
Yeah, no, we do work with ML frameworks just because they provide so much value.
Sure.
So yeah, for training specifically, so we
Uh-huh.
use TensorFlow a lot,
Uh-huh.
PyTorch a little bit too. I think it's mostly historical. And then for deployment though, for deployment we use TensorRT,
Uh-huh.
which is NVIDIA's deep learning inference library. And what's great is that it's really optimized for NVIDIA hardware, of course.
Uh-huh.
There's a lot of like, it's also optimized for inference. So
Uh-huh.
you can do some optimization of the graph, for example. And yeah, we deploy using TensorRT. So yeah, and we get pretty big performance gains with that.
Cool. Wait,
Yeah.
so is that the whole thing? So you sort of have data collection?
No, that's not all.
Oh, that's not
So
all? Wow, amazing. All right,
after training
what else
this,
do you have?
no, there's evaluation. So the
Yes.
validation of the model. So let's say you train one model that's doing
Uh-huh.
obstacle detection.
Yeah.
What you really want is like understand if the modification of that model, for example, is how is that going to impact the overall system.
Uh-huh.
That's a very tricky system that requires pretty fine-grained understanding of the impact. And so let's say we have this perception system that's a mix of kind of like post-processing, Kalman filters, neural networks, and so on and so forth. They're all mixed in pretty complex ways.
Mm-hmm.
What we want to do is like have multiple levels of KPIs and a pretty large breadth of KPI to understand what's happening in the system.
Mm-hmm.
That's the step number one. So for example, like false positive, false negative, sure, right? But
Yeah.
then we want the next level, which is at the perception API level, so like higher level, you know,
Yeah.
how many mistakes do I make per hour, for example,
Uh-huh.
right, of detection of a car. And then I also want to understand even further than that, how do I drive the car? So which involves simulation in that case. So we want to be able to run simulation jobs with this new perception system to understand like how the system behaves now with
Uh-huh.
the same simulation. So we want to do all of this. So we have a system to basically evaluate all of these things at scale together, which is on the same infrastructure. So like same data structures, you know, same dashboards, same kind of output data, same analytics library, and so on and so forth. And the output of this is like all these KPIs plus what we call events. A false positive is an event, for example. We can define an event as anything. Once we have all of this, then the AV developers can look at all this information, and this is the next step. This is what we call debugging, basically, which is also like software 2.0 based, right? Debugging the output of a predictor.
Yep.
And so we look at the output of the predictor, and we can look at the KPIs, look at the event, cluster the events, and then zoom in onto all of these events and like very fine grain look at them and the prediction versus the ground truth, for example, or like see if there's something missing when there is a lens flare. So we can go very deep and then come back high and then make a diagnosis about what's going wrong about the system. And this diagnosis is the kind of like how we improve the system. This diagnosis tells us like, I need more data on Japan at night, for example. And then we can go back to the curation step, which is building better data sets. So yeah, this is kind of like the feedback loop that goes from debugging to this curation step that helps us improve our perception system over time.
Gotcha. And so you basically can, your user could like automatically request like, give me more like, like bicyclists in the snow or something. And then like the curation step go out and look for more of that or like weight that more or something.
Yeah, exactly. I mean, based on what the curation can do, which could be geographical conditions or maybe temperature if we have access to that type of sensor. But yeah, definitely, yeah.
That's amazing. So I mean, how do you? I'm just trying to think, like putting myself in your shoes. Like, how do you approach like making such a sophisticated system on behalf of customers? Like, do you like build your own perception systems just to try your own software? How do you think about that?
At the bottom of this like end-to-end workflow, we have core components basically, which is our data platform and our workflow management system. And those two things are powering everything, right? To be able to write ETLs, be able to register data sets, for example, be able to perform queries of our data, and make sure that all of these things are traceable end-to-end, which is a major requirement for the autonomous vehicles industry. So that we can then, if there's a problem in the future, we can go back in time and understand everything that happened. So anyway, all those things at the bottom are powering the top layer and are pretty, pretty beefy and made for scale.
And so, sorry, the first thing is data storage. Did I have that right?
Yeah. Oh, it's data platform
Data platform, and then a workflow management system.
and then workflow management system. Yeah.
Gotcha. And so the data, what is it? So the data platform is like keeping track of where all the data is, or what does that do?
It's a bit more than that. So basically, it's all the infrastructure required in order to store structured data, structured and unstructured data.
Uh-huh.
Right. So structured data could be anything like I don't know, like simple floating points, continuous values, and raw data is like all the sensor recordings in general.
Right.
So we have all of this and we can organize it. And the second step is we want to be able to query all of this at scale.
I see.
And so basically we use Hive, we use Presto, we use Spark SQL and Spark in general to enable us to do all of this. And so this is what the data platform provides, all those pieces.
Uh-huh.
Yep. And then the workflow management is more around like the ability to schedule like those complex compute and data access tasks, right?
Uh-huh.
And stitch them together.
Yeah.
And so basically we know we can organize data in a certain way. We know we can access a cluster, but then we want to make sure that, like I explained earlier, we can perform those graph of tasks. And sometimes we require a lot of scale when we do evaluation at scale, for example, on like thousands of hours of data. And so we need a workflow system that enables us to do all of this.
Yep. Interesting. So I guess like one thing I didn't hear you say that I think a lot of people talk about is sort of synthetic data. Like, is that interesting to you? How do you think?
Yeah, no, it is. For so synthetic, we have a simulation, basically a simulation team. I think I mentioned it for testing purposes.
Right, for testing. I wasn't sure if that was like totally synthetic simulations or what.
And entire. Well, I mean, we can do both for open loop, which is no control and planning in the loop, like no actual driving.
Yeah.
We can replay existing data. So that's really good because then we can measure on real data. But for data like closed loop, which is really driving in a world, we need real simulated data. And this is where NVIDIA kind of shines because we can, of course, generate like simulated world, like in video games. And so even more than that, we have the ability to generate all kinds of sensor data for the car. So not just, not like also, LiDAR data, radar data, but also like CAN, IMU, all those things that are car specific. We can generate all of this, and we have a special box that we call Constellation, which has this generator, like simulation generator on one side, and what we call the ECU, like the embedded system on the other side, that can process all those sensor inputs in the same box. So basically do the exact simulation, right? Exact processing of the simulated data. So we can do all of this, and we can use it for testing. And we can also use it for, of course, collecting data and training on data that just doesn't exist in the real world, for example. Yeah. So very helpful for bootstrapping perception efforts, for example, bootstrapping new neural networks, right? And
so I guess, right. I mean, where do you plan to, I mean, it sounds like you have like almost a complete like end-to-end solution for people. Like, could I come to you and like, with a car and some sensors and like get a system that could make an autonomous vehicle for me?
Yeah, that's exactly, yes, you can, except that we need, I mean, it's difficult to change sensors, as you can imagine, because if suddenly we use a different sensor, we're going to have to recollect data to revalidate and retrain models or fine-tune them and so on and so forth. But assuming they're like similar to what we have, or that you're willing to pay enough money, we can redo that work entirely. Yes.
So I guess you're like the perfect person to ask, like, what do you think is like left to do to, I mean, I don't actually see, I live in San Francisco, so I do see autonomous vehicles driving around a fair amount. But like, what pieces do you think are left to really work on to make it like a real thing that, that I would use every day?
So you don't use it every day is what you're saying?
Well, I actually rarely go in an autonomous vehicle, and I feel like I'm in the industry. So.
Oh, I see. Do you? I mean, do you have a Tesla, like Model 3 or any?
No, I mean, I've played with them, and I think they're like very, very impressive. So I guess maybe that's a good point you're making. That, but like, what about I guess like, what do you think is the next steps with systems like yours? Like, what are you thinking of focusing on?
Honestly, I think so. First, I think this is going to be pervasive, and I think in the future, everyone's going to have like autonomous vehicle functionality.
Uh-huh.
That's number one.
Yeah.
But I think the vision goes even further than that. Is that cars are going to become software defined, or are on the way to becoming software defined, and that's like basically people are going to see a centralized computer with a really nice UI UX, right? And they're going to be able to buy new software potentially to upgrade their cars. And this is already what's happening with Tesla a little bit. And,
totally.
And I think that's probably one of the reasons why their capitalization is so high, their valuation is so high.
Yeah.
But the other car makers are also looking into that model, and like interested in it. And I think this is the future of the industry. So for us, I think this is also the future. And we need to be ready for this world at NVIDIA. So that means having like a programmable platform, an open platform, right? Because we want to enable all those car makers or tier one to build those systems together on the same chip, on the centralized computer. We don't want to exclude them basically from our chip, right? We want to enable people to write software on our chip, infotainment software, self-driving software, and so on and so forth, right? And now self-driving is so difficult that we can provide it for them, as a given application for big car makers or even smaller, and just like develop it as an application for them. And then where are we going with that? I think is a matter of like performance and improving the control planning and the entire perception system. I think we're still like at the beginning of it. We're going to be able to do better and better and better over time by building a lot of automation first, by potentially adding machine learning in areas that don't have machine learning yet, such as predicting the planning path, for example, right? Doing things like that. Anyway, that's pretty much it.
I guess what I'm hearing is like you think that there's sort of like iterative improvement in a bunch of different things, and then applying machine learning to planning is like the big like just sort of the next steps in making these systems work better. I'm curious, what do you think is the stuff that people are really like wrestling with right now to make these things really work?
I think the hardest thing is urban areas right now. So like being able to drive in urban areas, like in New York City, for example, it's really, really hard. And that's the next frontier. It requires all sorts of new signals coming from the car. Like for example, like intersections, lights, lack of lanes, right? Things like that can be very tricky, or like unknown kind of like vehicles, such as garbage collection, stuff like that, right? So all of this is still a little bit newer, and all the like self-driving providers started with easier areas, such as highways, except for some of the level 5, like Lyft, or Uber, or like the ones that are trying to already leapfrog that. That's a big challenge, basically. That's the next frontier, I think.
Do you feel like your approach at NVIDIA is significantly different from like Tesla or Lyft, or I mean, how do you think about that?
I mean, all these companies, they are targeting different things. So as a result, there are some differences. So Lyft is targeting level 5. They want to have fully autonomous vehicles. Tesla is building cars, so they don't need to build a platform that's usable by other people, for example. Right? On our side, we build a platform, and we make money with our hardware. We can also make money with our software, but our software has to be like usable by everyone else. So we have to make it in a way that is such, right? So this is one of the constraints we have. As a result, for example, the platform we're building, like the core infrastructure, is designed in a way that can be ported in other, like to car makers, for example, or any, right? Like people developing self-driving components.
Do you think your platform, I mean, it's interesting because all the pieces that you mentioned of your platform, I think like it's super relevant to like healthcare applications or almost like any kind of deep learning application. Like, how do you think about, would you ever expand your platform to other applications, or?
Yeah, I think that's possible. Some of these pieces are not required per se, and sometimes the scale we aim for is not required as well for healthcare, for example. And however, usually what we try to do is what we built is more like a superset of those tools and push the frontier a little bit further. Now some things are a little bit tied to autonomous vehicles, but the entire end-to-end workflow though seems very applicable. You're right. The tools themselves that we build sometimes were customized to the data we have. So yes, we could extend them. It would just require some work, basically. Yeah.
I see. I'm curious, this is a kind of a specific question, but I've been thinking about this lately. Like, how important do you think is the sort of hyperparameter search piece? Like, like the neural architecture search you're talking about? Like, is that really essential, or is that like a
That's
nice
a
to
good
have?
question.
Like, how?
So neural architecture search is well, it's still like something we're exploring. I think it can be important because we can really reduce the compute footprint
Uh-huh.
for us. So I think it can work. So for example, we can constrain the search space of our neural architecture search to something that's going to perform really well on target hardware in terms of latency.
Right.
Right? Because NVIDIA has like some hardware accelerators that are specific. And so we can make sure that we target this and find the architecture, and so on and so forth. However, hyperparameter search is something that we have available, but the kind of like the advantage of using that versus the compute it requires is often like not super interesting for right for developers. So we do it sometimes, but it's not really like a big advantage or a big competitive advantage, I would say, for us.
I see.
Yeah.
Is there a piece of your platform sounds amazing and it solves like, a whole slew of problems. Is there like a piece of it that you're like especially proud of that you think is like really like really stands out to you as like best in class or?
I really like the active learning part.
Totally.
And everything that goes around that, because so one other thing we are doing is what we call targeted learning, which is the ability to take perception bugs. So like, oh, I'm not able to detect, like trucks in that position, whatever. And then use that and sample a data set that then is going to be used for training and fix the perception bug. Right. So, and doing that is similar to active learning, but like conditional active learning. So I'm really proud of these two things because I really love the automation of it all, right? Like we could just go on vacation and be like, okay, now let's just the system work. We have like, customers sending their bugs and automatically we just fix them,
Cool. Well, this is so fascinating, actually. Even if we weren't recording this for something, I think I would have really enjoyed this conversation.
No. Thanks. I mean, I love talking about it.
Talk to you. Yeah, it's great to meet you, and thanks so much for doing this with us.
Cool. Well, thanks a lot.
All right. That was such a great conversation. Thank you, Lucas and Nicholas. I'm going to add a link to Nicholas's Twitter in the show notes below, and I would highly recommend that you guys check him out. Also, if you'd like to continue the conversation, we do have a very active Slack community with over 1,000 machine learning engineers, and I would love to see you guys on there. Finally, before we go, I would love to talk to you guys about something that I'm super excited about. So lately, we've been working with a lot of self-driving car companies at Weights and Biases, and that means that we've been building native support specifically for self-driving machine learning models. So now, with just a few lines of code, you can do object detection with 2D and 3D bounding boxes within Weights and Biases. You can also do semantic segmentation, so you can compare your model's predictions with the true labels inside your dataset. And finally, my favorite, you can now log point clouds within Weights and Biases. So that means you can now use point clouds to understand your scene with custom annotation layers. You might use this with something like a data set of LiDAR points. So for example, Lyft put out a self-driving car data set composed of LiDAR points, and you could plop that into Weights and Biases and draw nice little 3D bounding boxes around your cars, people, and other objects within your scene. It's a great time. I'm going to leave some links in the show notes below so you can try out point cloud, semantic segmentation, and also object detection. It's a really fun time, whether you're working on self-driving professionally or just for fun. I would love for you guys to try it and tell us what you think. Finally, you can also use Weights and Biases to run sweeps to tune your hyperparameters in a very organized way. This means that you can just give us a list of hyperparameters that you would like to search through and also a search strategy. And then we will go through and train all these different models and find you the best one in a very organized way, which is very low effort on your part. I'll also leave some links down below for you to try out our sweeps. That's all for today. We'll see you in the next episode. Have a nice day.